Welcome back to my XPUBlog series. I'd like to introduce you to SYCL queues, including how to pick which XPU we run our kernels on. This allows us control in ways that range from nonchalant to unmitigated control freak. It's a must-not-miss introduction to SYCL queues with my special rest of the story that you're not going to find anywhere else, including in our book. As is my custom, I have a QR code. It will reappear at the end of this video as well. It's the same as the clickable link under this video. Either one will take you to step-by-step instructions to make following along incredibly easy. In addition, the article the QR code takes you to will start with any clarifications or corrections for this video that I might add in the future. In prior videos, I reviewed our XPU programming goals. I shared how to get and use a DevCloud account. And together we lightened up a kitten with a Hello SYCL program. In this video, I'll introduce you to SYCL queues and device selection. In our book, we describe them first in Chapter 2. The concept of a queue is fundamental. For this video, I will treat devices as totally independent. In future blogs, we'll explore how SYCL has context that'll help us manage resources that might be shared between a collection of devices, such as memory. But for this video, we'll just focus on queues as a connection between a host and a device. When we create a queue, it creates a connection to one device. Once created, the device that that particular queue connects to cannot be changed. SYCL does allow us whatever level of control we desire as to which device a queue connects to. At runtime, our program can check what's available and make whatever choice we want, ranging from give us whatever's available to general guidance like I want to run on a GPU, or we can get as specific as we like. We can direct work to one queue, or we can split up our work and send it to multiple queues. We can decide which based on what machine our application is run upon. Now, two things that we throw into a queue are kernels of work, lots of them hopefully, and memory commands to move around data that the kernels need or have created. For purposes of programming, we treat an XPU as a black box that we feed with data and code to run. That code we call kernels. A queue is the host's only connection to asking an XPU to run code or to copy memory. At least initially. Truth be told, once we kick off a kernel using a queue, on some machines that kernel could then send information back and forth via shared memory forever and never really come back up for air. So technically speaking, a queue isn't as exclusive as I've made it out to be, but let's not dwell on that. Let's treat the queue as the all-powerful connection between a host and XPU that it should be normally in our programs. Everything we need is handled by only 6 different actions that are available for queues. 3 are about executing kernels, the other 3 are about managing data, in other words, memory. I promised to explain how we can pick which XPU we run our kernels on. In a prior blog, I presented a Hello SYCL that lightened up our kitten normal. In that program, I simply created a queue. That's the same thing as using a default selector. This is the nonchalant approach. It effectively says, use whatever you've got. This approach will always work because SYCL guarantees there must be a device available. I said always work. Well, the specification will require that of our implementation, but we can still cause it to fail if we don't install our drivers to make the installation complete. So a truly robust program should provide a try-catch around queue creation, even if a valid installation shouldn't fail. In addition to the default selector, SYCL allows us to ask for a CPU or a GPU or an accelerator. The latter category is kind of a catch-all for devices that aren't a CPU or a GPU. DPC++ also offers an Intel extension to request a real FPGA or an emulated FPGA. Now, since FPGA compilations are not known for speed, we will want to debug as much as possible using an emulator before checking code out on a real FPGA. Each of these selectors can fail if such a device is not on a system. For example, the GPU selector will fail on a system that has no GPU on it. It's easy to imagine many configurations are possible, and it's easy to imagine that we might have very specific ideas on our order of preference in picking a device if there's more than one XPU available at runtime. For instance, we might prefer a GPU with USM support over a GPU without USM support, or we might like to get a GPU with the largest memory, or we might prefer an FPGA over a GPU. That brings us to the ultimate selection method. We call it custom device selector. It might sound a little scarier than it is. We just simply write a routine that scores a given device. The routine can consider anything about the device that we wish, right down to its name or model number, as long as interfaces give us access to that information. If we return a -1 from our routine, it says don't select this device. Any positive value is a score. High score wins. The system will automatically call our custom device selector routine for each device that it knows about at runtime, and it'll pick the one which our routine gives the highest score to. Or, of course, it could fail if the best we give is a -1. This interface is very versatile, and it's just host code, so anything goes, including static and global variables, etc. And we're not limited to writing just one custom device selector. We have as much control as we need to handle selection at runtime, regardless of the machine our application happens to be run on. I wrote a simple example in the book, now known as Figure 12-3. In this example, GPUs are good generally, and if they have Acme in the name, they're definitely favored. However, any GPU that has Martian in the name is completely unacceptable. Okay, it's a little silly, but it illustrates the power of custom device selector. Acme or Martian name checks could easily be changed out for test for a particular feature we like or one we want to avoid. We could also consider multiple device types, and we could favor FPGAs over GPUs, for instance. So far, I've described how to select a device and create a queue to connect us. There are more parameters available that I'm not digging into in this video. Property list is one of them, and you can do in order property. That I will mention in a few minutes. An exception handler, well, those are discussed in chapter 5 of the book and definitely will be the topic of a future XPUBlog. Context are not discussed much in the book, so I'm going to start talking about them in my next XPUBlog when I talk about how I like to think in an abstract manner about possible machines to help my code be more portable. After that discussion in my next XPUBlog, it'll be much easier to explain context. Applying what we've learned so far, we can revisit our Hello SYCL program from the prior blog and change it to specifically target FPGAs. We simply change the queue creation to use an FPGA selector. You'll note I'm building my program statically for this one device. That gives us the ability to compile quickly if I'm not targeting an FPGA. As soon as I include an FPGA target, an FPGA compilation needs to happen. The FPGA code takes more than an hour to compile. It's not too bad for an FPGA compile. An FPGA emulator option lets us compile quickly while we're still debugging our program. Both of them use FPGA selectors, which are DPC++ extensions. SYCL encourages vendor-specific device types. And personally, I think after more users experience FPGAs with SYCL and FPGAs from multiple vendors, the SYCL standard might be ready to standardize this device type. But I like the idea of waiting until we're pretty sure we have a model that has consensus across many users and vendors. For debugging, we can use the FPGA emulator selector and use that on a system with or without an FPGA. We can use an FPGA selector, and then we'll have to run on a system with an FPGA. With neither defined, we're just going to compile and use a default selector, which should select the most performant device available, but it won't pick an FPGA because those are special. I have a step-by-step instructions laid out in the blog on how to build this program and run on an FPGA or the FPGA emulator, or use the default selector, just as shown in this code. Be sure to try it out. The only change to the code from the prior blog that we make is adding the selectors and changing the command lines to do the compile. Otherwise, our entire SYCL program remains exactly the same, and it runs and gets the same lightning of the kitten done using FPGAs. I have shown all the code changes here. I hope you'll try it out online. The Intel Dev Cloud has powerful Intel Xeon processor systems for compilation and emulation. It has FPGA systems to run FPGA compilations on it, and it has CPU and GPU systems that will happily run the default program. Unlike other devices, FPGA code needs to be compiled in advance for the device. This is simply because FPGA compiles are too slow to do on the fly every time we run our program. It is possible that other XPU devices may have heavyweight compilation processes too, so SYCL provides for this. But in general, code for many XPUs can be finalized for the device at runtime by just doing just-in-time compilation from an intermediate form into the precise code needed for that device. We dive into this more in the book. This figure from chapter 13 illustrates the key concepts at a high level. Now that covers the most critical elements to understanding SYCL queues. Now, for the rest of the story. What if we want to force a program to use a particular device without recompiling it, or passing a parameter to the program? In other words, can I limit what my program sees to be less than what's actually on the machine? Usually the answer is yes. There is no standard SYCL way to do this, but the DPC++ implementation does provide an answer. Other SYCL compilers may have similar mechanisms. For DPC++, the SYCL device filter environment variable can be set to limit the SYCL runtime to use only a subset of the possible devices. This can affect device query functions such as get devices and get platform, and it affects all the device selectors. Interestingly, on many systems, a single device might be supported by multiple drivers. For instance, an Intel GPU may have a level 0 and an OpenCL driver, both available at the same time. Other systems might have different versions of drivers installed simultaneously. All of this is provided for, and the SYCL device filter variable can affect which devices the program sees at runtime, and which drivers our program can interact with as well. This gives us control over what the program thinks is the full platform. Note, we can limit what devices are available to the program using the filter, but we can't force where it actually runs. The program still has to select a device at runtime and then choose to connect a queue to that device. All we're doing with the filter is limiting the choices the program has. So if I have a machine with multiple FPGAs, for instance, we could limit which FPGA our program sees, and that would be the only FPGA it could select from. In this way, we could compile one program that grabs the first FPGA it sees and runs on it. And if we have a system with multiple FPGAs, we would run different instances of that with the environment variable set for each one, telling it which one it had to run on. The URL shown here goes to the DPC++ LLVM project GitHub, where there's documentation on this feature. It also documents some very cool tracing options that can help understand behavior on specific systems during device discovery and selection. That can be helpful when we find ourselves puzzling about why something isn't quite working like we expected, or just to get the simple peace of mind that our program is running the code where it expects. You might be wondering if a SYCL queue is FIFO. The default queue style is not. SYCL does support in-order queues if we augment the queue constructor with the property in order. I did mention properties before, and this is a key usage for it. But the default and recommended queue does not guarantee order at all. This allows execution to proceed when safe and when the system chooses. The SYCL specification does not label a name on the default style of queue. You might call it priority queue or a ready queue, or maybe the most appropriately, it would be named a run queue. The key is that it's up to the implementation to decide the order to issue things to the hardware that it has received into a queue. The SYCL specification only requires that dependencies are preserved so that you don't do things out of order in a way that'll break. Now, beyond that, an implementation is likely to be concerned with matching hardware availability with the needs of ready-to-run requests. Of course, dependencies must be observed for correct execution. If kernel A writes data and kernel B uses the data, then obviously that requires that kernel A run before kernel B. SYCL does determine what it can automatically when we use buffers. Now, if we're sloppy, we can cause more dependencies than needed. For instance, if we label a buffer read-write but never change it, that creates a dependency that's artificial. Or if we have a huge buffer but only write a tiny part of it, we're creating more dependencies than necessary. That could affect performance. If we're sloppy in ways like that, our program may well run slower than it could otherwise. In addition to the dependencies that SYCL can determine automatically from buffer accessors, we can provide explicit information using depends on. It's safe. We can't break dependencies implied by buffer accessors. We can provide explicit information using depends on. We can't break dependencies implied by buffer accessors, and if we're using USM, we must use depends on for dependencies that are created through the use of USM. Of course, we could use in-order queues also to force ordering of our requests. A SYCL compiler will not figure out read-write dependencies for us when using USM. Other than dependencies caused from buffer usage, we have to explicitly inform the SYCL runtime of any requirements necessary for legal execution. In the book, we kind of dance around this while we're learning the basics of SYCL for the first 7 chapters, but then we tackle dependencies head-on in chapter 8. We'll revisit this in a future blog when we explore the pros and cons of buffers and USM for memory accesses. Regardless of the queue type, the host program proceeds without waiting, and queue operations finish asynchronously. This is very asynchronous. We can have our program explicitly wait or test for completions of kernels. Errors during submission are synchronous. Errors during execution of kernels are asynchronous. This makes sense since the execution of kernels is asynchronous as viewed from the main program. More about error handling can be found in chapter 5 of the book, and I will revisit in a future XPUBlog. Since I brought up the asynchronous nature of letting devices run wild and independent, I will mention that the SYCL specification offers 8 synchronization guarantees. There are guarantees of when the host synchronization will occur, as well as there are ways for synchronization to happen in kernels. Have you wondered if using multiple queues is ever better than one? The answer is it can be more convenient, and that can easily lead to better code. 2 common reasons to use multiple queues are, 1, when we have multiple threads or ranks in a program, because that can greatly simplify programming because we avoid coordination between threads or ranks when using a single queue. So it's encouraged in this situation to go ahead. You can have a queue connection to the same device from every thread or every rank if you want to. Or multiple in-order queues can be better than one because they'll express more parallelism. I would encourage everyone to just use default queues, not in-order queues, but if you prefer in-order queues, then you might consider using multiple in-order queues if that allows you to get more queues being used concurrently. This can express more parallelism. This also applies if we're using default queues and getting lax in our dependencies. Either way, multiple queues might offer a natural way to offer up more parallelism, and that's a good thing. It's really up to us to decide as programmers if having multiple queues to the same device is more convenient in our application or not. Either is fine, so it's up to us to choose what works best for us. You might wonder if multiple queues could be worse than one queue. No, you can rest easy. This should not be an issue. I could say, however, if a slowdown did occur when you were using multiple queues, I would be suspicious of 2 things. The first factor might come from the fact that contexts are not cheap to create. So I would check that I had not gone crazy creating an excessive number of contexts per thread. Right now, an implementation is likely to create a context for each queue creation, and that's probably not optimal. I'll probably revisit this in a future blog. The solution would be to create a context that was used by all the queues. A second factor might be multiple paths theoretically could be affected by command buffering, batching. It's a more complex interaction in the software stack and might send you digging into the platform optimization guides to understand. I would not rush to do that unless I was pretty sure I'd done all the other things I can to tune my application. I'm guessing that may be something I want to revisit in a future blog for fun as well. Once we realize we can point multiple queues at one device, it won't be long until we ask if we can point a queue at part of a device. The answer is yes. SYCL calls this a subdevice. A device can be subdivided and give us a queue for each division. In fact, we can still have the queue for the whole device, and we can use them in any order that we want. So the queue for the whole device would be able to issue to execution units across the device. Queues pointed at a subdevice will only have use of the subdevice. And some devices act exactly as devices, so they can even be divided up further. In my next XPUBlog, when I discuss abstract models for a machine, And for our application, the uses for subdevices will become more evident. This is a powerful mechanism and can be very useful. If we run multiple SYCL applications on a single host, each application is entitled to have one or more connections to an XPU. If we have multiple applications running, we will end up sharing a device. SYCL doesn't define, as far as I know, a specific API to query that a device is busy. Even if it did, we'd really want to know how much longer will it be busy, or how busy is it really. So for right now, the state of the practice is for a program to use what it finds. As I mentioned at the start of this rest of the story, implementations may offer ways to affect the environment that a specific program runs in to filter out devices and limit choices. This could be used to control which applications use which devices, if that level of control appeals to us. Now keep in mind that a single SYCL queue can only dispatch to a single device or subdevice. In case you were wondering, with SYCL today, anyone could write an abstraction to behave like a queue to spread work across multiple devices. Of course, the abstraction would need to use unique SYCL queues for each device. Generalizing this has a lot of difficulties, especially because of memory, so this would be some fairly advanced work that could be considered. However, with detailed knowledge of your own application's need, this might make sense to you. Lastly, I will note that the final SYCL 2020 specification caused a book errata. You can find the information in the SYCL spec in Appendix D about what changed, and what changed in this particular case is the concept of a host device went away. Now, all devices are still supported, but the host device concept was dropped in the final SYCL 2020 specification after our book went to press. It's the only significant change we didn't predict when putting content in our book. I have made a note of this in the errata for the book that we maintain along with the code examples in the GitHub project for the book. The errata list is pretty small, knock on wood. We always welcome feedback if you find any additional issues in the book. Now, back to the SYCL 2020 dropping of host device. SYCL still requires there always be some device, so our kernels can always run somewhere. The change, however, is that SYCL no longer requires a magical host device with specific properties. The concept of a magical device didn't fit very well with embedded platforms, since target machines can't always be expected to have the ability to even support such a device. So it was a good thing to drop. I think this is a great example of how SYCL is serious about being cross-platform. As I mentioned briefly earlier, if no drivers are installed that can run a kernel, then the guarantees of SYCL don't even matter and our program can still fail. That is true with or without the concept of a host device. So anywhere we mentioned host device in the book, we are sorry. It turns out dropping it was an improvement and doesn't matter. In general, if you thought you wanted a host device, you probably want to find and use a CPU device. And now you know the rest of the story for SYCL queues. That was a quick look at how SYCL helps us control which XPU our code runs on. SYCL allows us whatever level of control that we desire. At runtime, our program can check what resources are available and make the choice we want. We can say, give us what's available, or I want a GPU, or we can get more specific. We can direct multiple collections of work to the same device or multiple devices. We can decide where we want our work to go depending on what's available on the machine our application runs on. And we learned how queues connect our host program to XPU devices and looked a little more deeply with the rest of the story. In my next XPUBlog, we will consider how to simplify our thinking about hardware and software, getting an abstract model of the machine. This will help not only with our sanity, but it will lead to more portable and maintainable applications. It'll be a must-not-miss explanation of how to think clearly and program well in SYCL. Remember to subscribe to my XPUBlog channel so we can explore heterogeneous programming together. Follow the QR link or the link below for easy step-by-step follow-along instructions, and look there if there are any clarifications that I add about this video. Please leave comments and suggestions there as well. No topic is too big or too small to suggest as we explore XPU programming together. I look forward to your feedback and suggestions.